Hi everyone. In today's video, we are going to be discussing the routh-hurwitz stability criterion. So, what if I told you could determine whether a control system would blow up or behave perfectly well without solving any single differential equation? That sounds impossible, right? But the routh-hurwitz stability criterion allows you to do this. It allows you to determine the stability of a control system by just looking at its characteristic equation. So in the next minutes, my team members will break everything down step by step. It will tell you the whole idea behind this routh-hurwitz stability criterion, the mathematics involved, and also some real-world examples. So let's get started.
Classical control system, we have three types. One, the system being stable. Two, the system being marginally stable. And then three, the system being unstable. So when we talk about the system being stable, what we are trying to say is that after the step bounces, the system returns back to its desired output. But with the marginally stable, the system oscillates, that is, it never settles down. And for the system being unstable, that is, the system grow without bounds, that is, the system breaks down. Classical.
So, quick question. Who actually came up with this method? In 1877, a British mathematician named Edward Routh published his stability criterion. But here is the thing. He was originally trying to analyze spinning tops and planetary orbits, not circuits, not control systems, just planets. Then in 1895, routh-hurwitz, working completely independently, derived the exact same results, and neither man knew what they had done. And the favorite part is, before computers existed, this was the method engineers used to design entire control systems by hand using nothing but this table. No MATLAB, no Python, just a pencil, and a criterion.
Please, my name is Osei Theodosia Mensah. Then I'll be helping us to draw the routh-hurwitz array. So the question we were given was 2s to the power of n plus 5s cubed plus 5s squared plus 2s plus 1 is equal to 0. This was the equation. To draw the routh-hurwitz array, we start from the highest power to the lowest power. So we have s to the power of 4, s cubed, s squared, s to the power 1, and s to the power 0. Also, when writing the values, we usually leave a space in between. So for this one, we would have 2. We'll jump the 5 and then write the next 5. Then we'll jump the next 2 and then write 1. For the s cubed, we would write the 5s cubed. Then we'll jump this 5 and then write the 2 for the 2s. And then we'll jump this 1, the next digit is 0. For the rest, we would represent them with variables. So we have b1, b2, c1, c2, and then d1. So this is what our array looks like. First, finding b1, we would use 2, 5, and then 5, 2 to find our b1. So 2, 5, and then 5, 2, with 5 being our pivot element. So to find b1, we have 5 times 5 minus 2 times 2. Then we divide this by 5. Computing this, our answer would be 4.2. So that's the value of b1. To find b2, we would use 2, 5. To find b2, we would use 2, 1, and then 5 0. So B2 2 1 5 0. So computing that, we have 5 by 1 minus 0 by 2. Then we'll divide by 5 to give us a value of 1. For C1, we would use 5, 2, and then B1 and B2 to find C1. So C1 would use 5, 2. B1 was 4.2, and then B2 was 1. So computing this, we have 4.2 times 2 minus 5 by 1, then we divide through by 4.2, and then the answer we would get for that is 0.8095. Then to calculate for C2, we would use 5 0 and then B1 and a 0 here. So C2 have 5 0, B1 was 4.2, then the 0. To calculate our C2, we have 4.2 times 0 minus 5 times 0, then we divide by 4.2, and then the answer for this 0 real number is 0, so we have C2 to be equal to 0. So lastly, we'll calculate D1 using B1, B2, C1, and then C2. So we have 4.21, 0.8095, and 0. So we have 0.8015 times 1, so 8095 times 1 minus 0 times 4.2. Then we'll divide through by 0.8095. So our final answer for D1 would be equal to 1. So to rewrite our array, we have s to the power of 4, s cubed, s squared, s to the power 1, s to the power 0. So 2, 5, 1, 5, 2, 0. B1 was 4.2, B2 was 1, C1 was 0.8095, C2 was 0, then D1 was 1. So this is how we find our routh-hurwitz array. Thank you.
So in this section, we are going to really answer our question, is our system stable or not? To do that, we need to remember that we need to look out for sign changes first of all. Why do we need to look out for sign changes? The routh-hurwitz criterion tells us that the number of sign changes within our column of values, the first column of values, directly corresponds to the number of poles in the right half of the S-plane. So looking at our values, moving from the top to the bottom, all the values remain consistent in the positive range, meaning there are no sign changes whatsoever, which means that there are no poles in the right half of the S-plane. Why are we checking if there are poles in the right half of the S-plane? So in control systems, poles in the right half of the S-plane show instability, as such that the system will grow uncontrollable over time, which we term as instability. So if there are no poles or all the poles lie in the left half, it means that our system will be able to withstand whatever disturbance or inputs that comes. They will naturally decay over time. So now we can confidently say, as there are no sign changes in our first column of values, that our system is stable. To better understand this concept, in the next section, we will dissect a hypothetical situation to get a better grasp of this concept.
So, our system passed, but let's make sure we really understand why by looking at what failure looks like. Imagine a different system where the first column came out as 2, 5, negative 3.2, 1.9, and 1. Going down 2 to 5, there will be no change in the system. Going down from negative 3.2, there will be a slight change in the system. Now, from negative 3.2 to negative 1.9, there will also be another change in the system. And from negative 1.9 to 1, there will be no change in the system. 2 changes in the system, 2 poles in the right half S-plane. That means the system becomes unstable. The sign changes and the red flags. 0 flags and then you are good. Any
One of these application areas is the aerospace. So in this area, every autopilot system must be provably stable. Now, the routh-hurwitz method is one of the tools that engineers use to ensure this. They ensure that the flight control surfaces of these systems won't cause oscillation that can damage the aircraft. Another application area is in power systems. So in these systems, the electrical grid controllers must be stable in order to prevent cascading failures. This is because even a single unstable controller can trigger blackouts across an entire region. We also have it in robotics too. We have its application where drone altitude control runs on the principle of stability. So if these drones are unstable, they flip and crash within seconds of takeoff, and that's something we really don't want. We also have it in automotive systems. An example is the self-driving vehicles. So in these vehicles, we have stability in them in order to prevent the system, or we have stability controls in order to prevent the system from overcorrecting itself and then causing accidents. Now, classical controls is not something old or irrelevant, but rather it is the foundation of every engineered system that needs to behave responsibly.
Solving every stability problem in sight. Let me save you some pain. Mistake 1. Skipping the coefficient check before you build a single row. Verify that all the coefficients are positive and none are missing. If they are not, the system is already unstable. Don't waste time on the table. Mistake 2. Arithmetic errors that cascade. Every row depends on the one above. One wrong number poisons everything below. Work carefully. Check twice. Mistake 3. The special case. What if you get a 0 in the first column of an intermediate row? You can't divide by 0. The fix is called the epsilon method. Substitute a small positive value, epsilon, complete the table, and take the limit as epsilon approaches 0. It's a clean workaround. Just know it exists.
Alright, so I'm Joao Prempeh and I'll be leading you through even as we summarize and the complete routh-hurwitz criterion in 3 steps. Yeah. So from all the analysis and with the transfer function given, we've been able to know that there are 3 basic steps to explain and to demonstrate this routh-hurwitz criterion or the module. The first thing that we have to take note is that when given a transfer function, you should be able to write the characteristic equation from it. And based on that, we are able to build our root array, that is row by row. And to do that, we also establish that using cross multiplication formula is the best, because the cross multiplication formula allows you to check all the calculations carefully. And finally, to conclude, we also looked at the count sign changes. Yes. And we were able to know that this tells us exactly how many unstable poles your system can have. And with that, we can actually make an analysis. In the case where we have 0 sign changes, we can tell that our system is stable. In other cases too, we can also make an analogy and see that it is unstable. So it is clear that this model helps us to really understand classical control systems. Although it looks simple, it is powerful because it is basic in the design of engineering system. that is, which help us to know how stable or unstable a principle can be. That is based on just a function given. Thank you very much.